Welcome to Module 3, Wells and Production Forecasting. In Module 2, we developed an understanding of the reservoir and generated dynamic model forecasts. In this module, we convert those forecasts into a practical development plan. We'll look at how wells are designed, where they are placed, how production profiles are built, and how these forecasts become the foundation for facility sizing, economics, and development planning. The key question throughout this module is simple. How do we turn reservoir potential into producible barrels? The dynamic model tells us how the reservoir is expected to behave. The wells plan determines how we access that reservoir. Several decisions must be made. How many wells are required? What type of wells should be drilled? Where they should be located? In what sequence they should be developed? And how they should be completed. These decisions are closely linked to production forecasting. In general, more wells can increase production rates and extend plateau production, but they also increase capital expenditure. This is why wells planning is fundamentally an optimization problem. The objective is not to maximize well count. The objective is to maximize value. Not all reservoirs require the same type of well. The simplest option is a vertical well, which is often suitable for thick and laterally continuous reservoirs. A deviated well follows an angled trajectory to reach targets away from the surface location. A horizontal well maximizes reservoir contact and is especially effective in thin reservoirs or unconventional developments. The most complex options are multilateral and extended reach wells, which allow larger areas of the reservoir to be accessed from a single surface location. The choice of well architecture depends on both reservoir geometry and development constraints. The goal is always the same: maximize reservoir contact while maintaining economic efficiency. The same well architectures can be used both onshore and offshore, but the constraints are very different. Onshore developments often use pad drilling, where multiple wells are drilled from a single location. Wells can frequently be added as new information becomes available. Because drilling costs are relatively lower, operators have greater flexibility to modify the development plan over time. Offshore developments are less flexible. Platform slot numbers are often fixed during project design, and drilling rigs may be contracted years in advance. For subsea developments, every additional well brings extra infrastructure requirements such as tiebacks, control systems, and manifolds. As a result, offshore projects place much greater emphasis on getting the initial well count correct. This is another example of a principle we've seen before. Onshore development is generally more flexible, while offshore development requires greater certainty before sanction. Every well drains a portion of the reservoir. If wells are placed too close together, they compete for the same hydrocarbon volumes. This is known as interference and can reduce the effectiveness of each well. If wells are placed too far apart, portions of the reservoir may remain undrained or production may be unnecessarily delayed. The challenge is finding the optimum spacing. Operators may also use infill drilling later in field life to recover volumes that were not effectively drained by the original development plan. An important point is that optimum recovery does not always mean drilling the maximum number of wells. Sometimes it is more valuable to wait for additional production data before committing further capital. Drilling a well is only part of the process. The reservoir must also be connected to the wellbore through an appropriate completion design. In conventional reservoirs, this may involve perforations, open-hole completions, and sand control systems. In low-permeability reservoirs, hydraulic fracturing is commonly used to create flow paths and increase productivity. In more complex developments, intelligent completions may be installed. These systems use downhole valves and sensors to control production from multiple zones remotely. The key idea is that completion design has a direct impact on production performance and ultimate recovery. Most producing fields follow a similar production profile consisting of 4 stages. The first stage is ramp-up, where wells and facilities are progressively brought online. Next comes the plateau, during which production is maintained at or near the maximum sustainable rate. Over time, reservoir pressure declines and water or gas production increases, leading to the decline phase. Finally, the field enters a tail production phase, which may be prolonged through infill drilling, artificial lift, or other optimization measures. This production profile is one of the most important outputs of the FDP because plateau rate and plateau duration strongly influence project economics. As reservoirs mature, natural reservoir pressure often becomes insufficient to bring fluids to the surface. Artificial lift systems are installed to extend productive life and maintain production rates. Common examples include electric submersible pumps, gas lift, and rod pumps. The choice depends on reservoir conditions, well characteristics, and operational constraints. For offshore developments, reliability becomes particularly important because interventions are expensive. A key planning consideration is that artificial lift requirements should be anticipated early. Supporting infrastructure such as gas compression for gas lift must often be included in the original facility's design. Just as reserves and volumes are expressed as ranges, production forecasts should also be expressed as ranges. The P90 case represents a conservative forecast and is often used for minimum commitments and downside planning. The P50 case represents the best estimate and typically forms the basis of the FDP. The P10 case represents the upside potential of the asset. These forecasts are direct outputs from the uncertainty ranges developed in the subsurface model. The important message is that a production forecast should never be treated as a single guaranteed outcome. It is a range of possible outcomes that reflects the remaining uncertainty in the reservoir. This slide brings together several concepts from the module. The first image illustrates the different well architectures, from vertical wells to more advanced horizontal and multilateral designs. The second image shows the typical production profile, including ramp-up, plateau, and decline phases. The third image demonstrates how well spacing affects drainage and interference between wells. Together, these figures summarize the key relationship between well design, reservoir access, and production performance. The Permian Basin is an excellent example of manufacturing-style development. Wells are commonly drilled from multi-well pads using standardized designs and established type curves. Because individual wells are relatively inexpensive, operators can continuously adjust drilling programs based on commodity prices and field performance. Fast cycle times allow companies to learn from new wells quickly and incorporate that information into future development plans. This flexibility is one of the defining characteristics of unconventional onshore development. Many offshore fields in Southeast Asia are too small to justify standalone facilities. Instead, operators often develop clusters of small fields around a shared host platform. Wells from surrounding satellite fields are connected through subsea tiebacks to central processing facilities. In this type of development, the wells plan and facilities plan must be optimized together. Host platform capacity, tieback distance, and well count all influence each other. This is an important reminder that well planning cannot be performed independently of concept selection. The wells plan directly affects project economics. Well count and drilling schedule determine a major portion of project capex. The production profile determines when revenue will be generated and therefore plays a major role in NPV and payback calculations. Facility capacity is typically designed around the P50 production forecast while considering flexibility for potential upside cases. This slide also provides the bridge to Module 4. The subsurface model defines the opportunity. The wells plan defines how it will be produced. The next step is selecting the development concept that can support that production strategy. Let's summarize the key messages from this module. Well architecture must match reservoir characteristics and development constraints. Onshore developments typically treat well count as a flexible variable, while offshore developments often fix well count at sanction. Well spacing is an optimization problem that balances interference against undrained reserves. Production profiles consisting of ramp-up, plateau, and decline phases drive both facility sizing and economics. Finally, production forecasts should always be expressed as P90, P50, and P10 ranges to reflect uncertainty carried forward from the subsurface model. In Modules 2 and 3, we developed the subsurface understanding and the wells plan. The next step is deciding how those wells and fluids will actually be developed and processed. Module 4 focuses on development concept selection, where subsurface requirements, wells planning, and facilities design are brought together to identify the optimal development solution. This is often the highest value decision made during the entire field development planning process.